well, why can't we just store some water that's at the right elevation? So why can't we design these filter boxes so that they're deep enough so that they can lift the water back up into a storage tank? And I have a little schematic of that on the right. And the filters slowly fill that box up with water as they're filtering it. And then of course, excess water goes to the town, but they make that storage tank full. And then when it's time to backwash, you draw water from that storage tank to backwash the filter. And this also seems like a very nice idea, but if you do the math and you figure out how big does that storage box have to be, it turns out it ends up needing to be bigger than an agua clara plant just to store the water to clean one filter. And so that ends up not being a great option. So we're down to nothing works. We can't think of any options that actually are viable. And so that's why we go with, we have to invent something new. So why is this difficult? It's because of backwash. It's because we need to clean these filters. And the underlying issue is that there's a big difference between the flow rate during backwash and the flow rate during filtration. You need to have a lot of water, a high flow rate, in order to lift all that sand. So if we could somehow get the filtration velocity and the backwash velocity to be closer to being the same, then we wouldn't need a set of 6 filters. But that's not easy either. So it's invention time. So what we're going to do is we're going to do a little geometric trick. So on the left is the design by Cepis, where they have 6 filters working together, 5 of them backwashing 1. And on the right is this idea of, instead of having these 6 filters set out side by side, let's put them on top of each other. So there's the idea of stack. Let's put all those filters on top of each other and put them all inside one box. And then there's some craziness. As you can see, there's water entering in this top inlet. There's water entering in a middle inlet here, another middle inlet, and then a bottom inlet. And then the water, in all cases, the water flows through one small layer of sand and then exits through an outlet. So there's water exiting here, here, and here. So that's this idea of stacking the filters where there's maybe, we use 1.2 meters of sand in that filter box, and each filter is actually 20 centimeters. There's 6 of them all working in parallel when it's filtration time. And then when you backwash, you change it so that you turn off all the inlets and outlets. So there's no arrows shown on any of these inlets or outlets because somehow we've turned them off. And all the water is going in through the bottom. And so now the same amount of water that we had going into this filter before, instead of it going into 4 inlets and going through 6 layers of sand in parallel, it's now all going in through 1 inlet, and it's going through all the sand in series. So you see how we switched it? We went from 6 filters in parallel to, during backwash, it's 6 in series. So the water is going through all of them. And so the water is going through 6 times faster, and we've got our backwash velocity. I'm ready for a question if anybody wants to hit me with one. Are you good with the little trick of switching between parallel flow and series flow? And then maybe the mystery is, how do you inject water into a sand bed? Okay, and then on this slide, I'm addressing another issue, which is Well, where do you get the water to backwash it? And we're going to play another trick because it just makes it so much simpler. Instead of using filtered water to backwash this filter, we're going to use the same water that we would normally be filtering to backwash it, meaning that we're using clarified water to backwash it. And you might say, oh, but the clarified water is not really clean. Well, but actually the clarified water has a turbidity that's somewhere around 1 NTU. And in some parts of the world, like in Honduras, 5 NTU is the drinking water standard. So it's below the drinking water standard in many parts of the world. And I've had water that was just flocculated, flock filtered, and settled to drink. And there, we actually have some towns in Honduras that is the only treatment. They don't actually have water, they don't have filtration, they just have flocculation, flock filters, and sedimentation followed by, sedimentation followed by disinfection. So we're using pretty clean water to backwash this filter, and then we will filter to waste after backwash so that you dump the very first water coming out of the filter. And it turns out, and you can check my math on this, but the fluid residence time, the water residence time in the filter when you're in filtration mode is just, I think just a little bit over a minute or just a little bit under a minute. It's right around a minute. So it doesn't take long at all to flush the previous water that was in the filter out after backwash. And so the fact that you used settled or clarified water as your source water for backwash is not a problem. This filter has the same flow rate and water source during filtration and backwash. You don't need any storage tank at all to backwash the filter. The water that's coming from your clarifier is what you're using to backwash the filter. So here's the whole water treatment plant with the filter tucked in there. So let's trace what's happening in the plant. Here are coagulant and chlorine stock tanks that are elevated so that they're at a high enough level so that they can be pushing those chemicals through our dose controlling system and can be dosing the coagulant up into the pipe leading away from the linear flow orifice meter into the flocculator, or they can dose the chlorine over here on the filter. So here are the constant level tanks that are used to set the level of the chemicals that are being used to feed the chemical doser. Yeah, I know it's really tiny, but right there's where the chemical dose lever system is hiding. And then here's the entrance tank. Let's see, it's actually the water in this entrance tank is entering right here, going through a trash rack right here, going past the doser where the doser is setting its level based on the flow through the LFOM. Water leaves the LFOM and goes down into the upstream end of the flocculator, goes over all of the baffles in the flocculator. In this case, it's 2 channels, and then enters the inlet channel for the sedimentation tanks, goes down through the sedimentation tanks, goes back up through the flock filter, through the plate settlers, out through these effluent manifolds, through orifices, into the channel that has the clarified water. And then I don't show it in this design because I'm still figuring out how to do this. There's going to be either a pipe or a channel that takes the water from this channel that has the clarified water in it over to this channel, which is the inlet channel for the filter. And then it's going to go through the filter. Okay, we have 2 filters, which is part of the idea that you really should have 2, which is just like the CEPI's design having 12. you see that? We said that the CEPI's design, where they have 6 filters working together, they really ought to have 12, so that when you have a low flow condition for your plant, you can still backwash your filters. Same thing here, just that we get that same benefit by having 2, because each of our filters has essentially 6 filters inside of it. And we can always turn one off and send all the water through the other one to backwash it under conditions of low flow. Anybody want to ask a question about how the water goes through the plant? We're all good. So now some more details about the stacked rapid sand filter. Let's see. We're going to talk about the controls. This whole set up here are the controls for getting the water into and back out of the filters. And as you can see, there's a ton of pipes. There are pipes that are inlet pipes and outlet pipes. And if you're remembering how this works, there's the inlets and outlets are every other pipe. So the top pipe is an inlet and an outlet, inlet, outlet, inlet, outlet, inlet. The bottom one is the one that is also used for backwashing. And because the backwash flow ends up being 6 times as much, the bottom pipe ends up being often, not always, but often ends up being a bigger size to handle that higher flow rate. Other kind of fun things that are going on here, the sand in the sandbox is in this box. It's also full of pipes, right? There's going to be lots of pipes inside the box in order to distribute the water and basically inject the water into the sand. And that means that if you ever need to, or when you need to do any service inside the filter box and you want to get the sand out, you can't send workers into that box and give them a shovel and tell them to get the sand out, because the box is actually full of pipes. And so from the very first filter, we knew we had to have a mechanized way, not automated, but a mechanized way of getting the sand out of that sandbox. And the way that we do that is there is a pipe coming out of the very bottom of the sandbox, and it's just like one straight pipe. In this iteration, we don't even have a valve on the end of it. And this is like, there's a little, it's called a Fernco fitting. It's a little like rubber gasket that goes around a pipe, and it has 2 hose clamps that tighten it on. And when they want to empty the sand out of the filter box, they will loosen up those clamps, and this red cap on the end of the pipe will pop off. And what they do is they set the filter up in backwash mode, so the sand is fluidized. And now there's all this fluidized sand that is just happy to flow up this pipe instead. And so it dumps the sand into the sand channel. And so you can empty out the filter. And I guess, you know, if you want to make yourself infamous, you go into an agua clara plant and you open that up when they're not expecting, because it dumps the sand out. And then there's a whole heck of a lot of work to put it back in again. There should be like a lockout on that pipe, so you don't accidentally do that. Another thing that we're adding, that we have not yet built the plant that has the ability to recycle the backwash water, but for your assignment for the design challenge for filtration, I'm going to have you calculate the turbidity of the backwash water. And it turns out that it's less than 100 NTU. And treating 100 NTU water with an agua clara plant or a standard municipal water treatment plant that has flocculation and sedimentation, treating 100 NTU water is just a lovely experience for the operators. It's super easy to treat 100 NTU water. It's actually it's often easier to treat 100 NTU water than it is to treat water that's like 2 NTU. So that means that the backwash water is actually highly treatable. It's not that dirty, and it's a crying shame to waste it, especially if there's a drought. And so we're adding a backwash recycled tank that will take the water from the backwash, store it in that tank, and then before you backwash the next filter, you would use an electric pump to pump that water back up to the entrance tank of the plant. And now you're probably all in shock, right? Because Monroe began this talk by like preaching against the use of pumps. And now I just kind of like slide it in that we're going to use a pump for this. Is Monroe just completely inconsistent? Okay, so I'm not actually inconsistent. What my line is, I want to be able to operate the plant and provide folks with water without using electricity in the plant. Except for lights, another one. I like lights in the plant too. Okay, so the backwash water flows through this backwash siphon, which we'll talk more about that, and it ends up in this channel. So that's the level that the backwash water is sitting at. And if you want to recover that backwash water, you pull this little pipe stub out, this red pipe stub, and that pipe is connected into this tank. And so the backwash water will flow into that tank instead of being dumped.